In this chapter, we're going to talk about one of the most important concepts in all of chemistry, which is the mole. We're going to talk about what a mole is, all the different conversions between other units that we may measure and the mole, how to perform those conversions, how to do multi-step conversions. We'll talk about how to use the mole concept to figure out what the formula of a molecule is if we're told what percentage each element makes up in that compound. So you are going to need something to write with. You're going to need something to write on. You will need your periodic table. You will need a calculator. Once you have all those things ready, let's go. So if you recall back when we were calculating average atomic mass, we used a unit called the AMU, or atomic mass unit. The thing is, it's a unit that's completely made up because we just didn't want to have to deal with the fact that like a proton weighs 1 times 10 to the minus 27th kilograms or something along those lines. What it would be really nice for us to do, though, is have a way to relate our AMU into an actual measurable amount of mass in grams. That's where the mole comes in. The mole is basically a conversion. It's saying, here's how many particles you have to have for a substance's atomic mass in AMU to equal its actual mass in grams. The conversion that we use for this is we use what's called Avogadro's number. For any substance, 6.02 times 10 to the 23rd particles is the same as 1 mole of that substance. That means if I were to have, for example, sodium atoms, 6.02 times 10 to the 23rd sodium atoms is 1 mole of sodium. If I have water molecules, 6.02 times 10 to the 23rd water molecules is equal to 1 mole of water. A way to think about a mole is think about a mole like a much larger version of a dozen, right? A dozen is always equal to 12. For us, a mole is always equal to Avogadro's number of pieces. And this is nice and all, but we still can't measure particles in a lab, right? Let's get to some actual conversions that would make a little bit more sense for us. So how about we try converting this into grams, right? Because that's what we're going to measure most often in a lab. What we do for that is we use a substance's molar mass. The molar mass, very simply, take the atomic mass of every atom in the formula, add them together, and get your final answer. So we'll do, as an example, the molar mass of glucose, which is C6H12O6. We'll take carbon. There are 6 atoms of carbon in 1 molecule of glucose, or we could also say there are 6 moles of carbon in 1 mole of glucose. So I'm going to take 6, multiply it by the atomic mass of carbon, which is 12.01. I'm going to take hydrogen, so 12 times the atomic mass of hydrogen, which is 1.01. And then I'm going to take oxygen, 6, times the atomic mass of oxygen, which is 16.00. I'll multiply all of these out, and then I'll add them together, and I'll get a final value of around 180 grams per mole, which is the unit for molar mass. You'll also see this phrase, by the way, referred to as molecular weight or formula weight or gram atomic mass. So those are different names that you'll see for this same unit, but it's not terribly hard to do. Like I said, just multiply the subscript by the mass of the element from your periodic table, add them all together at the end, and you're done. So that's how we convert between moles and grams. Another measurement we might want to make is if we're doing work with gases, we may want to figure out what volume of gas we have. Now, for what we call an ideal gas, and we'll get into what ideal gases are a little bit later once we talk about gas laws. So for any ideal gas at what is called standard temperature and pressure, or we abbreviate it STP, which means 1 atmosphere, which is normal atmospheric pressure, which you're feeling around you right about now, unless, of course, you're watching this in the middle of a hurricane, and 0 degrees Celsius. At those conditions, 1 mole of any gas, regardless of which gas it is 22.4 liters. Now, one of the reasons why we can say it doesn't matter what gas it is, every gas occupies the same volume, is because gas particles are really tiny and they're extremely far apart, so we're going to assume that they don't really contribute to the volume of the sample. So for our dimensional analysis, we need an equality. Well, here is our equality for moles. 1 mole of any substance is Avogadro's number of particles, whether it's atoms or molecules or ions or whatever. That is also equal to the molar mass of the substance measured in grams. That is also equal to 22.4 liters for any gas measured at standard temperature and pressure. If you're doing a mole conversion, all you have to do is pick whichever 2 of those are relevant to the problem and use those to make your conversion factor. So if I want to convert for, let's say, between liters and grams, I could just use the 22.4 and the molar mass to convert between those two. And I can do that as a one-step conversion. If you wanted to, you could go from liters to moles and then moles to grams as a two-step. Some people like doing that. Whichever way you want to do it will be perfectly acceptable. And one thing to keep in mind is that as we go through this throughout the year, we're going to be adding more things into this equality. Right? We're going to add in what happens if we have solutions, concentration of a solution. What happens if we have a gas that's not at standard temperature and pressure? We may start talking about, for example, the number of electrons transferred inside of a reaction and how that adds into this equality. So there are a bunch of things we'll add to it. So this will grow over the course of the year. Just remember, pick the 2 that are relevant. So how about we try an example? So our example, we have 24.31 grams of water, and I want to know how many molecules that is. Right, so the way that I'm going to do this is I'm going to start off by writing the amount that I'm given, so 24.31 grams over 1. I want to cancel out grams, so grams is going to be in the bottom of my conversion factor. I want to go to molecules, so I'm going to put molecules at the top. And notice how I'm writing water for both of these. Whenever you're giving me something involving a substance, it has to be amount, unit, and then the substance that you're measuring. And now I plug in my conversions. So for my molar mass, H is 1.01, but there are 2 of them. Oxygen is 16. That adds up to 18.02. And for my molecules, I want Avogadro's number, 6.02 times 10 to the 23rd. If it's in the numerator, I multiply. If it's in the denominator, I divide. So I'm going to do 24.31 times Avogadro's number divided by 18.02. And that's going to give me a final answer of 4.62 times 10 to the 24th molecules of water. So that's a mole conversion. We just converted from grams into molecules. In our next video, we're going to talk about how to figure out percent composition of a formula, which is just telling us how much of a formula, for example, in water, what percentage of it is hydrogen, what percentage of it is oxygen as a function of its mass.